Meeting is now being recorded.
Hello, and welcome to the 11th webinar in the Measurement Error webinar series. I'm Kevin Dodd with the Division of Cancer Prevention at the U.S. National Cancer Institute. Today we'll be hearing from Dr. Larry Friedman about combining self-report instruments and biomarkers, but before we get started, please note that the webinar is being recorded so that we can make it available on our website. All phone lines have been muted and will remain that way throughout the webinar. Following the presentation, there will be a question and answer session, so please use the chat feature to submit a question. You can find the slides for today's presentation on the website that has been set up for serious participants. Now, it's my pleasure to introduce the presenter for today's webinar. Dr. Lawrence Friedman is the director of the Biostatistics Unit at the Gertner Institute for Epidemiology, where he directs a research and consulting program in biostatistics and advises the government on public health policy. Larry has previously worked for the British Medical Research Council and the U.S. National Cancer Institute, where he was acting branch chief of the Biometry branch from 1993 to 1996, and was part of the team that developed the Women's Health Initiative and the AARP Nutritional Cohort Study. He was founding co-editor of Statistics in Medicine and has also served as co-editor of Biometrics. As I mentioned, today Dr. Friedman will discuss combining self-report dietary intake data and biomarker data to reduce the effects of measurement error. But on one final note, Dr. Friedman is joining us live from Israel. We're hoping that the telecommunications links will be kind to us, but if we do lose Larry, we will endeavor to get him back on the line with as little delay as possible. Okay, Dr. Friedman.
Thank you very much, Kevin, and I'm pleased to actually be broadcasting on this occasion. The last lecture that we had, there was a little hitch at the beginning. Anyway, good morning, afternoon, or evening to everyone. For me, it's late afternoon. Today, I'm going to be describing methods for combining data from dietary intake self-reports with dietary biomarkers with the object of reducing the errors in dietary intake measurement. This series is dedicated to the memory of our dear colleague, Arthur Shatskin. And here is a list of the presenters and collaborators in this webinar series. So, my aims today are firstly to give you an understanding of the motivation for combining self-reports with biomarkers. Secondly, to describe methods of combining these sources of data together with their aims and the information that's required to implement each method. And thirdly, to show you the potential gains as well as the limitations of each method. So we'll start with a general introduction. To understand why we would want to combine self-report data with dietary biomarker data, we need to go back to some of the lessons that we learnt in lectures 6 and 7 of this webinar series. Then we learnt that when self-reports are used in the study to investigate a diet-health relationship, the measurement error in the reports causes, firstly, the risk estimates or odds ratios to be attenuated towards the null value, and secondly, study power to be decreased. And these effects are a direct result of the loss of information about usual dietary intake that occurs due to the measurement error. Now, both last week's lecture by Doug Mithune and my lecture today discuss how we might recover some of the lost information. Last week, Doug Mithune explained how combining different self-report instruments can help to recover some of the lost information and thereby alleviate the attenuation of estimated relative risks and loss of study power. Today, we'll learn how combining self-reports and biomarkers can also help, although we will see that some of the conceptual and statistical issues are different from those involved in combining self-reports. To place our discussion in a clear context, suppose we are conducting a nutritional cohort study in which we have particular interest to relate usual intake, denoted by T, outcome is a binary variable indicating diagnosis of a specific disease. And as we have noted before in this webinar series, we can't measure usual intake exactly, and we obtain instead a self-report. And here we will assume that it is a food frequency questionnaire, and we will denote the reported intake by Q. We'd also suppose that the association between the health outcome and the usual intake of interest is a logistic regression, as described in this equation. As just mentioned, Y denotes a binary health outcome, and T denotes the true usual intake of the dietary component of interest. The Z's in the equation denote other exposures, confounders, effect modifiers, or mediators. And in particular, we'll be talking quite a bit today about confounders and mediators. The alpha coefficients in the equation are the log odds ratios corresponding to each explanatory variable, and we'll be particularly interested in estimating the log odds ratio alpha subscript T for the dietary intake. We cannot obtain an exact measure of the usual intake, T. Our problem is that if we use our food frequency report, Q, in its place, then our estimate of the log odds ratio alpha T will be attenuated. In Lecture 7 of this series, Doug Mitsune explained the method of regression calibration, which is used to de-attenuate the estimate of the log odds ratio and thereby give an unbiased estimate of the log odds ratio alpha T. The method entails using not the food frequency report Q as our measure of usual intake, but the expected value of usual intake conditional on Q and on the other explanatory variables in the model, denoted by the symbol shown here, E for expectation of T, the usual intake, given the values of Q, the reported intake, and the confounder Z. You can think of this expression as the predicted value of true intake, given our knowledge of the reported intake and other explanatory variables. Although regression calibration successfully removes bias from our estimates of log odds ratio, it unfortunately usually has no impact on the second problem caused by dietary measurement error, the loss of study power. In fact, regression calibration usually makes little or no change to the result of the test of significance of the log odds ratio, and if the result is non-significant using the attenuated estimate arising from entering the self-reported intake Q into the logistic regression model, then it is usually also non-significant using the regression calibration adjustment. In fact, in a very small proportion of cases, a result that is statistically significant using the unadjusted method can become non-significant using regression calibration. Now, the reason that regression calibration usually has no impact on the problem of lost power is because it uses the same information about dietary intake, essentially the value of the self-reported intake Q, as does the unadjusted method. So in order to improve the study power, we need to bring in additional information about dietary intake. And in this lecture, we will consider doing that through a dietary biomarker whose value we will denote by M. We're going to consider two rather different approaches to combining information about dietary intake from self-reports and biomarkers. The first and simpler approach we call the direct approach. These methods are relatively easy to use and can sometimes recover lost power but they are not guaranteed to do so and sometimes actually cause extra loss of power. In addition, they do not yield unbiased estimates of relative risks or odds ratios. The second approach, which we call the modelling-based approach, and it will normally recover some of the power lost through dietary measurement error, and will also give unbiased estimates of relative risks or odds ratios. It therefore carries substantial advantages over the direct approach. However, unlike with the direct approach, to implement the modelling-based approach, we need to supply information on the relation between the biomarker and true usual intake, and the necessary information is not always available. Before we get into the methods of combining biomarkers with self-reports, we need to review briefly some background regarding dietary biomarkers. A dietary biomarker is any biological measurement that is related to a dietary intake. Two main classes of biomarkers have been recognized. The first class, which have been termed recovery biomarkers, are those that are in a sense ideal in that they measure a certain dietary intake with little or no bias. Unfortunately, only a few are known. The remaining biomarkers that form the great majority of those available have been termed concentration biomarkers. The recovery biomarkers are called that because they are based on the recovery of specific biological products related to intake, directly related to intake, and they are not subject to large inter-individual differences in metabolism. By their nature, they measure short-term intake. The three that are known are doubly labeled water for energy intake, 24-hour urinary nitrogen for protein intake, and 24-hour urinary potassium for potassium intake. Besides measuring intake with minimal bias, they also have the important property that their errors are independent of true intake. The concentration biomarkers are called that because they are usually based on concentration of specific chemicals or compounds found in the blood, urine, or tissues. They are related to dietary intake, but not in a straightforward manner. And because of the complex metabolic processes underlying them, they could depend on dietary factors other than the target component, or on non-dietary factors such as hormone levels, or gender, or smoking. And this is a large class, including serum lipids, carotenoids, vitamins, and metals, among others. The recovery biomarkers have been extremely useful in the evaluation of self-report instruments, as we have already explained in lectures 6 and 7 of this series. They could also be used potentially in combination with self-reports, using the same methods as was described by Doug Mithune in the previous lecture, with the object of increasing precision in measuring dietary intake. However, this latter use is limited by their high cost or difficulty of specimen collection. The concentration biomarkers can also be combined with self-reports, also with the object of increasing the precision in measuring dietary intake. And that's what I'm going to describe to you now. As I mentioned earlier, there are two main types of methods for combining concentration biomarkers with self-reports. The first type of method, which is the simpler one, we call the direct method. Suppose we are interested in the association between a health outcome, denoted by Y, and intake of a specific dietary component, denoted by T. We cannot measure T, but we obtain a self-report from a food frequency questionnaire, denoted by Q, and also a dietary biomarker, whose value is denoted by M, the dietary biomarker being a biomarker for that dietary component. In the usual approach, we investigate the association by regressing health outcome Y on the food frequency questionnaire value Q, together with some known confounders Z. And this approach, we know, involves loss of statistical power due to the measurement error in the self-reported intake. So instead, because we have the biomarker measurement available as well, we can try combining it with the self-report. And I'm going to describe two ways of doing this. Firstly, we may use principal components. The principal components method is a way of forming a set of linear combinations of a core set of correlated variables so that the combinations themselves are uncorrelated. The first component is always the one that has the highest variance possible and is often used to serve as a summary measure for the full set of variables. Accordingly, we take the first principal component of the pair of variables Q, the self-report, and M, the biomarker, as our measure of dietary intake, and use that together with the confounders Z in the regression model for the health outcome Y. Secondly, we can use Howe's method. This involves taking the sum of each participant's ranks according to each variable Q, the self-report, and M, the biomarker. This sum is then entered into the regression of the health outcome Y together with the confounders. I will spell out both of these methods in greater detail in just a minute, but first I want to make a few general points about them. There are several advantages and disadvantages of these two approaches. Firstly, the estimated coefficient of the combined intake variable is not adjusted for measurement error, so it's likely going to be attenuated. However, note that the combined variable itself has no recognized units, and so the actual value of the estimated coefficient is not of intrinsic interest. What is of interest is its sign and whether or not it is statistically significant. Secondly, in some but not in all circumstances, the method will recover some of the power lost due to measurement error in the food frequency questionnaire. Thirdly, we do not need any external information regarding the relationship of the food frequency questionnaire or the marker to true usual intake. The method can be used just on the data observed in the study. And fourthly, we need all participants to have a marker value M as well as the self-report Q and the health outcome Y, although small amounts of missing information can be accommodated. Before we proceed to an example that illustrates these methods, there are a few notes on each that will be helpful to those who want to use them. We start with the principal components method. In the case where there are just two variables, the self-report and the marker, the first principal component takes a very simple form. It is the weighted sum of the two variables where the weight is the inverse of the standard deviation of the variable. This is shown in the formula shown here. The formula holds if the two measures are positively correlated. And if they are negatively correlated, then instead of the sum, we take the difference, as shown here. And then, as previously explained, once we have formed the principal component variable and calculated it for each participant, we enter it together with the confounders into a regression model for the health outcome and test whether its coefficient is significantly different from 0. Howe's method for two variables may be thought of as a non-parametric version of the principal components method. The way it's performed is as follows. First, the participants are ranked according to their self-report values Q, and then the same is done according to their marker values M. Then each participant's ranks on the two variables is summed, giving a result denoted by H for how. Finally, as before, H is entered with the confounders into the regression model for the health outcome, and the regression coefficient for H is tested. We'll now look at an illustrative example taken from an ancillary study of the Women's Health Initiative known as CAREDS, where the interest was in associations between carotenoids and eye disease. There were 1,802 women in this ancillary case control study, and the eye disease of interest in our example is nuclear cataract. The carotenoid intakes of particular interest are lutein and zeaxanthin, which are combined for our analysis. So available in this study were a food frequency questionnaire report on these carotenoids and also the serum levels. The most important confounders were age and smoking, and we restrict our analyses to these in our example. This slide shows a table with the results of applying the usual regression analysis to the data in this study based on diet self-report alone, compared to the principal component analysis and the how method. The second column shows the estimated odds ratios of nuclear cataract for lutein and zeaxanthin. Remember that I mentioned earlier that the units of the combined measures were not really meaningful. To overcome that, we have expressed the odds ratios to compare the risk of individuals at the 90th percentile of measured intake with the risk of those at the 10th percentile, using the control group to estimate the percentiles. You can see that with the introduction of the marker information, either using principal components or Howe's method, the estimated odds ratios become stronger, that is, further from unity than the unadjusted method. And in the fourth column, you can see that there are more highly statistically significant values with the principal components and Howe method, -3, compared to the unadjusted method, -2. From these z-values, one can also estimate the sample size savings that could accrue from the marker information, and that's shown in the last slide. This last column tells us that by including the marker data, one could obtain approximately the same power as in a study with just self-report data, but with only 45% of the sample size. Although the previous example shows that the direct approach to combining self-reports and markers can yield useful results, to get the full benefits of adding the biomarker information, one needs to take a modeling approach. As I've already mentioned, the direct approach carries several disadvantages. Firstly, it does not always lead to increased statistical power, and sometimes its use can lead to further loss of power. For example, if the biomarker has a weaker relationship with the health outcome than does the self-report, then power will be lost by combining them. Secondly, the estimated odds ratios are attenuated, and no correction is made for that. And thirdly, as I mentioned earlier, the combined measure of marker and self-report does not have any recognized units. All of these difficulties can be overcome in a modeling approach, but in doing so, we have to consider some more complex models, including issues of causality, and that's what we will do now. This is a causal pathway diagram that describes relationships between dietary intake, biomarker, and health outcome. Starting with the box for the true dietary intake and following its arrows, we see that the model postulates that the intake T causes a change in the biomarker M. True biomarker level here is denoted by M subscript T. This in turn affects the health outcome Y. In addition, the intake T can also affect the health outcome through pathways that do not involve the biomarker. As with previous models that we have considered, there are confounders, Z, and these affect the health outcome as well as the dietary intake or the marker or both. And lastly, the true intake is not observed but is reflected by the self-report Q, and similarly, the true value of the biomarker, which we denote by M subscript T, is not observed but is reflected by the measurement of the marker denoted as before by M, that is the value that we obtain from our assay. The pathway diagram that you've just seen actually includes a number of important assumptions that we are making in adopting such a model. The main assumptions are, firstly, the dietary intake causally affects the biomarker level. Secondly, the biomarker may at least partially mediate the effect of dietary intake on the health outcome. This seems reasonable when the biomarker is a serum or tissue level of the dietary component of interest. And thirdly, the main confounders are known and measured exactly. This last assumption is the strongest of the three, and indeed the greatest challenge to the reliability of results that use dietary concentration biomarkers is the question of whether we can identify the important confounders. The pathway diagram that you've just seen can be described by 4 different statistical models, all acting together, and they are shown on this slide. The principal model is the health outcome model, shown here. It describes the way that dietary intake T, the biomarker M subscript T, and the confounders Z jointly act to influence the health outcome Y in the form of a logistic regression, assuming here that the health outcome is a binary variable indicating disease status. The second model describes how the dietary intake T and the confounders Z influence the biomarker M subscript T. Here, as in the health outcome model, it is important to know and measure the main confounders. The third model describes how self-reported intake Q is related to true intake T, and is similar to the measurement error models that were described in lectures 6 and 7 of this webinar series. And the fourth model describes the measurement error for the measured biomarker. Note that here we assume a classical measurement error. In other words, we assume that the measured biomarker M is an unbiased measurement of the true biomarker level M subscript T, with random errors that are independent of the true biomarker level. The next set of 4 slides will show which parts of the causal pathway diagram represents each of the 4 component models whose equations you have just seen. In this first diagram, you'll see the health outcome model component comprising all of the arrows leading to the health outcome box. Each of the arrows carries the coefficient of the variable in the regression model. So, for example, the arrow from true intake to health outcome carries the coefficient alpha 1. And this next slide shows the marker intake model with the arrows leading from true dietary intake and the confounders to the biomarker level box. And this slide shows the model for dietary self-reports, showing the relationship between reported intake and true dietary intake. And this last slide shows the classical measurement error model relating measured marker to true biomarker level. And the number 1 denotes the coefficient for m subscript t in that model. So having described the postulated causal model that underlies our measurements, we must now address what risk parameter we are interested in estimating. Because of the complex causal model, this is not quite as straightforward as in simpler situations where we usually want to estimate a simple odds ratio or relative risk. To make the discussion simpler, we'll for the moment forget that we have error-prone measurements and suppose that we can measure true intake and the true biomarker level. And this slide shows such a model. The coefficients in the health outcome model, the alphas, and the marker intake model, the gamma, are shown beside the relevant arrows as before. And also for simplicity, we have omitted the coefficients of the confounders. You can see that there are two separate pathways from intake T to health outcome Y. One goes directly from T to Y and is known as the direct effect. Its magnitude is given by the coefficient alpha 1. The other pathway goes through the biomarker and is known as the indirect or mediated effect. Its magnitude is the product of the coefficient for the arrow going from T to MT and the coefficient for the arrow going from MT to Y. In other words, gamma 1 times alpha 2. According to the model, when a unit change is made to intake T, the total effect on outcome Y is the sum of the direct and indirect effects. In other words, alpha 1 plus gamma 1 times alpha 2, as shown in the bottom line of this slide. We call this total effect of diet on health, the total effect of diet on health outcome. And for a logistic model, it is the log odds ratio for a change in intake of 1 unit. It is this total effect that we are usually most interested in estimating, and we will denote it by the symbol alpha 1 star. Our object is to estimate it and also to test whether it's equal to 0 or not. When there is no measurement error, there is a much simpler way of estimating the direct effect than estimating each of the parameters alpha 1, gamma 1, and alpha 2, and then calculating alpha 1 plus gamma 1 times alpha 2, according to the formula shown just a second ago. Instead, all we have to do is ignore the biomarker and use a simple model relating health outcome to dietary intake, retaining the confounders as shown in this slide. If we do that, then the coefficient for the intake is indeed the total effect of intake on health outcome, the alpha 1 star that we mentioned just earlier. Unfortunately, when there is measurement error in the dietary intake, matters are no longer so simple, as we will see. So in the next section, we're going to consider various methods of estimating our target parameter, the log odds ratio for the total effect of the dietary intake on disease risk. We're going to consider 4 different methods or estimates of our target parameter. The first, that we call the unadjusted method, is the usual one of entering the self-reported intake Q, together with the confounders Z, into the logistic regression model for health outcomes. We learned in Lecture 6 that this gives attenuated estimates of the log odds ratio and loses power because of the measurement error in Q. The second estimate comes from the usual regression calibration method, where we enter into the logistic regression not the self-reported intake Q, but the expected or predicted true intake given the values of the self-report Q and the values of the confounders, which we denote by the symbol E of T, expectation of true intake given the values of Q and Z. The coefficient of this variable in the logistic regression then serves as our estimate of the log odds ratio. We learnt in Lecture 7 that this method will give us an unbiased, that is de-attenuated estimate of the log odds ratio, but it will usually not recover any of the lost statistical power. The third method we call enhanced regression calibration, and it is very similar to the usual regression calibration method, except that we use the biomarker M as well as the self-report Q and confounder Z in order to predict the true intake T. This is denoted by this expression, E of T, expectation of true intake given the values of the self-report Q, the biomarker M, and the confounder Z. As before, the coefficient of this variable in the logistic regression gives the estimate of our targeted log odds ratio. And this method was suggested by Prentice and colleagues in a paper in the American Journal of Epidemiology in 2009. The fourth method, which we call the new method, uses the full health outcome model that we considered in an earlier section, which includes as explanatory variables the dietary intake, the biomarker, and the confounders. To obtain unbiased estimate of odds ratios from this model, we need to use the regression calibration version of it. That is, we enter for the dietary intake the predicted intake, true intake, given self-reported intake, measured biomarker and confounders. And for the biomarker, we enter the predicted true biomarker given the measured biomarker, self-reported intake, and confounders. Having obtained the estimates of the log odds ratios alpha 1 and alpha 2 for the dietary intake and biomarker respectively, we then calculate the log odds ratio of the targeted parameter as alpha 1 plus gamma 1 times alpha 2, as explained previously. This slide illustrates the first three of these methods graphically. Essentially, we are leaving the biomarker out of the model and relating true dietary intake to the disease with control for confounders, as shown in this diagram. The three methods differ only in the measure that is used for the true dietary intake. We use either Q for the unadjusted method, the expectation of T of the true intake given Q and Z for the regression calibration method, and the expectation of true intake given Q, M, the biomarker, and Z for the enhanced regression calibration method. The new method uses the full causal model that we described earlier, estimates the relevant odds ratio parameters, the alphas and the gamma, and computes the targeted log odds ratio in the manner already described. So we first need to understand which of these methods gives us biased estimates of our target parameter and which gives us unbiased estimates. This question can be answered by some theoretical statistical work, and we have also checked it out with simulations. The theory tells us that the unadjusted method is biased unless, of course, there's no measurement error in the self-report, as we've already learnt. It also tells us that the usual regression calibration method is unbiased, which we have also learnt previously. The new results are firstly that enhanced regression calibration gives biased estimates of the targeted log odds ratio whenever there is some mediation of the dietary effect through the biomarker. And the other new result is that the new method gives estimates that are unbiased. Okay, so far we've been talking quite theoretically. Let's see how these methods are implemented in a real example. We're going back to the CARID study that I described to you earlier, when we were looking at the simpler direct approach to combination of self-reports and biomarkers. Just to remind you, the disease outcome Y is eye cataract. The self-reported intake Q is the logarithm of the food frequency questionnaire report of lutein and zeaxanthin combined. The biomarker M is the logarithm of their combined serum level, and the confounders are age and smoking. And here once more are the definitions of the four methods of estimation that we have just described. Now, to implement the second, third, and fourth methods, we have to compute the predicted true intake T using either just the self-report and the confounders, as in regression calibration, or the self-report and confounders and biomarker for enhanced regression calibration. And for the new proposal, we also have to predict the expected value of the true biomarker level. These predictions are all made through what we call calibration equations. Whether these calibration equations can be built at all will depend on the external information that is available. Usually what's required are one or more feeding studies to relate the biomarker level to the true intake, and one or more population-based studies to obtain population means and standard deviations of biomarker levels and self-reported intakes. Fortunately, these are available in the cases of lutein and zeaxanthin, and references to these studies are shown here. Using the information reported from these studies, we first built three models, one describing the relation of marker to true intake, and the other two describing the measurement error in the self-report and in the measured biomarker. A while ago in this lecture, you may remember that when describing the full causal pathway graph underlying the relationships between dietary intake, biomarker, and disease, we saw that the graph actually comprised four models. The three models shown in this slide are actually specific versions of three of those four models, with the health outcome model as yet being unspecified. So we see here a marker intake model, and here a measurement error model for self-reported intake, and here a measurement error model for the biomarker. The parameters of these models, including the variances of the random error terms, are all based on the information from the references shown in the previous slide. Note that we assume that these models are not modified by the confounders in the health outcome model, age and smoking. Although we cannot be certain that this assumption is true, the available references unfortunately did not provide information on this issue. Once those three models have been constructed, it's a relatively simple statistical task to convert the models into calibration equations using also information from the CARED study itself on the relation between the confounders and the self-reported intake and measured biomarker. The calibration equations are shown in this slide. You can see that each is a linear equation including self-report Q, confounders D, and except for usual regression calibration, also the biomarker M. It can be noticed in the equations for the new method that when predicting true dietary intake, the biomarker and the self-reported intake are both influential. You can see that their coefficients are large, 0.515 and 0.242 respectively. However, when predicting the true biomarker level, the measured biomarker level is highly important with a coefficient of 0.769, and the self-reported intake has little influence with a small coefficient of 0.051. The confounders also have relatively little contribution in these predictions. Once we have these calibration equations, we can implement the four different methods, and this table shows the results obtained from them when applied to the CAREDS data. You can see in the first row of the table that the estimated log odds ratio from the unadjusted method is much smaller than for the other three methods, displaying the attenuation that we would expect to see. The two unbiased methods, regression calibration and the new method, yield similar estimates, whereas enhanced regression calibration gives a slightly larger value, and we're going to consider the other columns of the table in the next section. The conclusions from this analysis so far in relation to the strength of the association between lutein and zeaxanthin intake and eye cataracts are as follows. Firstly, both usual regression calibration and the new method are for this study theoretically unbiased and produce similar estimates. We could therefore take the estimate of the log odds ratio as minus 0.45, midway between those two estimates, and this translates into an odds ratio of 0.73 associated with a doubling of the lutein zeaxanthin intake. And the calculation for this translation to the odds ratio associated with the doubling of the intake is shown on the bottom line of this slide. So far, we've concentrated on how to use modeling to estimate the targeted odds ratio. We now turn to hypothesis testing, and particularly to the question of statistical power to detect the odds ratio as statistically significant. We want to test whether the targeted log odds ratio is 0 or not. The four methods of estimation that we have considered all lead naturally to a method of testing this hypothesis. All that we have to do to convert the estimate into a test is to consider the ratio of the estimate to its standard error and to compare this ratio to the standard normal distribution. So here's the same table that I showed you just before for the CARED study example. Previously, we concentrated on this column, the log odds ratio column. The third column shows the standard error of each estimate, and the fourth column, their ratio, the z-value. And I've added an extra column at the end that shows the p-value, and we'll consider the actual values in just a minute. But first, we have to ask the question, which of these tests is a valid test of the null hypothesis? In other words, for which of these tests is the probability of rejecting the null hypothesis equal to approximately 5% when the nominal 5% level is used. And, of course, the null hypothesis is true. One might expect that the test would be valid only for those methods that give an unbiased estimate of the log odds ratio. However, the surprising answer is that all 4 tests are valid. And the reason for that is that when the null hypothesis is true and the log odds ratio is really 0, then all of the estimates become unbiased and will on average equal 0. Even the unadjusted estimate and the enhanced regression calibration estimate that are otherwise biased. So since all 4 tests are valid, the next question to ask is which of them is statistically the most powerful? In other words, which of them is the most likely to detect an odds ratio that is truly different from unity? And the simple answer to this question is that the enhanced regression calibration method is the most powerful of the 4 tests. And we see this fact reflected in the table of results for the carried study example. The enhanced regression calibration method leads to the most extreme z-value and to the smallest p-value. The intuitive reason for this gain in power over usual regression calibration is that using the marker in addition to self-reported intake to predict true dietary intake has increased the precision of our predictions, and the more precise estimates of true dietary intake then increase the power of detecting the association with disease. If we want to translate this advantage in power to potential savings in sample size, then we can consider the inverse ratio of the squares of the z-values for the 2 methods. For usual regression calibration, the z-value is minus 2.07, and for enhanced regression calibration, it is minus 3.15. The inverse ratio of their squares is 0.43, meaning that it's estimated that in order to achieve the same statistical power, a study that incorporates the biomarker in the prediction of true intake would require only 43% of the sample size required in a study that does not incorporate the marker information. Computer simulations that we have conducted indicate over a range of circumstances that enhanced regression calibration is the most powerful approach, and these results are presented in a paper in Press in the American Journal of Epidemiology. So our overall strategy that we recommend based on this work is that for estimation, the targeted odds ratio should be estimated by usual regression calibration, or the new method that we have proposed. And for testing the null hypothesis of no association between dietary intake and health outcome, the enhanced regression calibration method should be used. One question that arises from these results is why should we bother using the new method at all, when usual regression calibration gives an unbiased estimate and enhanced regression calibration gives a more powerful test? In fact, we will see in the next section that there is a situation where the new method is the only one of the 4 methods that provides an unbiased estimate of the risk parameter. Actually, there are a number of important issues that need to be considered when thinking about using biomarkers in the manner we've described. The first 2 points are raised by some work reported by Prentice and colleagues in the American Journal of Epidemiology in 2009. They considered a situation where they wished to use body mass index rather than a typical biomarker in their prediction of true dietary intake. Their context was the association of total energy intake with a variety of cancers, and in the diagram here we take breast cancer as one of their primary interests. The causal pathway diagram shown here is almost the same as the one that we have considered in this lecture, but there is one important difference. Notice that there is now an arrow leading from true marker, or true body mass index, to the self-reported intake, Q. This is because of the often observed phenomenon that obese persons tend to underreport their dietary intake more than the non-obese. In our models, we have assumed no relation between the biomarker and the measurement error. In these circumstances, as indicated in the title of this slide, the usual regression calibration method gives a biased estimate of the targeted log odds ratio. So when this situation occurs, the only unbiased method of estimation available to us is the new method, the fourth and last of the estimation methods that we described earlier. I should also mention that all four methods of testing the null hypothesis remain valid in this situation, but that enhanced regression calibration remains the most powerful. Another point raised by the application considered by Prentice et al. Is that there may sometimes be uncertainty regarding the direction of the causality. In the example where body mass index is used in the position of the biomarker, it's not entirely clear whether it acts as a mediator, as shown here, or as a confounder, as shown here. The dilemma is portrayed by the question marks in this diagram. In this case, it's unclear how to proceed. If body mass index were a mediator, then our target risk parameter should be the total effect of dietary intake on breast cancer. And we could use the methods described in this lecture. However, if body mass index were a confounder, we should be interested in a different target risk parameter, the effect of diet adjusted for body mass index. And then the estimation procedure would be different. If we cannot resolve the causal pathway question, then we cannot decide what to estimate. An important practical question is that of the cost of including a biomarker in the study. To implement the methods described today, the investigator needs to be able to obtain a biomarker measurement from any person in the study. This means that biological specimens have to be stored for all participants. The cost of taking and storing the specimens needs to be weighed against the sample size savings that could accrue from their use. It's actually the taking and storing of the specimens that is crucial in terms of cost. The cost of performing the assay is less crucial, since typically the number of assays that is done can be drastically reduced without loss of power by using a case control design nested within the cohort study. Today there are many prospective studies which are designed to include a blood or tissue bank, and in such cases the methods I've described may give very useful increases in statistical power for addressing questions of diet health associations without involving a large extra cost. Perhaps the greatest challenge to the successful use of concentration biomarkers in the manner we've described is the challenge of adjusting for confounding. As soon as we enter a biomarker into the model, we introduce a potential new set of confounders, and we can never be sure that we know what these are. Thus, associations that we see may sometimes be spurious, as we will find out to our cost if we try to build intervention programs based upon them. So extra care is needed in interpreting the results. Finally, as mentioned earlier, the modeling methods, enhanced regression calibration, and the new method require extra knowledge beyond what will be available from the study in question. In many cases, that knowledge may not exist, and new feeding studies may be required to provide it. Prentice and colleagues are currently conducting a large feeding study to identify new biomarkers of dietary intake and to enable the development of new calibration equations for predicting a wider range of dietary intakes. If that study is successful, then the methods that we have described today may become central to future nutritional epidemiology. So to summarize, usual regression calibration does not usually increase the power to detect diet-health outcome relationships. We've learned that using biomarkers can sometimes increase that power. Simple methods such as Howe's method or principal components can be used and are sometimes successful, but they do not guarantee increase in power and can sometimes even reduce it. More complex methods such as enhanced regression calibration can yield important gains in power, but require considerable extra information regarding the relationship between the biomarker and dietary intake. And the methods require availability of biological specimens for the individuals in the study and may be feasible in prospective studies that have incorporated biobanks. Thank you, and I'd be happy taking questions.
Thank you, Larry. We'll now move on to the question and answer period of the webinar. And several questions have come in as you were speaking. I'm going to try to, but they all seem to be very related to one another, so I'm going to try to make a sort of a gestalt question about all of them. And it relates to the choice of confounders Z in the various models and kind of how all those work together. First, can the set of confounders be different for different parts of the modeling exercise? Well, I'll let you answer that question first, and then I'll go on.
Let me see. I think there would be a possible situation where you had different confounders for the marker intake model and from the health outcome model. In other words, there may be confounders which are important in the health outcome model which are not important in the marker intake model. And in fact, that was a situation which we used in the Carr's example, that we had confounders in the health outcome model, age and smoking, and they were not used in the marker intake model. I think we would have liked to use smoking, but we just didn't have enough information in it. But it is quite possible that there would be markers confounders which are relevant to the health outcome model, but not to the marker intake model.
And following in that same vein, is it the case that are there ever some cases where there might be a role for some additional covariates that help with the prediction of, say, the biomarker, but don't actually come into the health outcome model?
Yes, indeed, that is a possibility. And of course, the real example is the questionnaire itself, which comes into the prediction for the predicting the dietary intake, but is not included in the as a variable in itself in the model.
Okay.
In the health outcome model. If there are several variables like that, they could all be entered, but the important thing is that their relationship to disease is disease is conditionally independent on them given the true intake, and in that case they can be used for predicting true intake, and not included in the health outcome model.
I think, and that was motivated by two of the questions that came up. One was, I think, was a good one, where the supposition that the same confounders might affect, like for example, markers or covariates for metabolism that might affect concentration biomarkers might not affect the dietary intake, and so those additional metabolic covariates would probably be used in the biomarker model, but not used to predict diet from the FFQ. Is that correct?
That's correct. Absolutely right. Yes.
Okay. And then another question that's related to this is you had mentioned in a footnote that all these models assume that the measurement error is not affected by the confounder Z, and I think that kind of goes with the fact that you're using regression calibration for these sort of things. But what happens, or can you give a little discussion of what might happen or how you might try to adjust these models if Q is affected, if the measurement error in Q is affected by the confounders?
If the measurement error is affected, say Q is affected by the confounders, and you knew how, and you could measure the confounders, then you would be able to take it into account by including that those confounders in the measurement error model. And if you did that, and then you would largely overcome this problem. If you were not aware of it, but they nevertheless did affect the measurement error in the self-report, then I would think that there will be a potential bias, but we haven't studied how large those biases might be, and it is a concern that needs to be looked at.
Okay. A couple of other minor points. Earlier on, when you were talking about the direct methods, housed and the PC method and the unadjusted, you showed a table, I think it was slide 27, that showed that you were looking at odds ratios from going to the 90th to the 10th, or the 10th to the 90th percentile of measured intake. Now, did those percentiles change depending on what you were using, whether you were using the principal component or whether using the house sum of the ranks as your dependent variable, or was that all based upon some standardized value of intake?
For each variable, the variable itself is used in the control group to find out what the percentiles were of the 10th and 90th, the 10th and 90th percentiles in the population. That's why the control group was used, on the assumption of a fairly rare disease. And of course, because in one case you're using the self-report, and in another case you're using the Howe measure, which is a sum of ranks, and in another case you're using principal components, which is a weighted sum of a biomarker and a self-report. Each of them has different percentiles, but what's common to them is that every time you are comparing somebody who's sitting at the 90th percentile compared to the 10th percentile in the population, if people are ordered according to each of these variables.
Okay, and the last question. Can you talk a little bit about the possibility of extending these methods to apply to some non-FFQ self-report instruments like food records or 24-hour recalls as the measured dietary exposure that's not the biomarker?
I think they could be used equally well in that situation. The only proviso is that the external information is available if we're talking about the modeling methods. And generally speaking, when it comes to doing population studies, and we need to know what the distributions of these instruments, the intakes reported on these instruments are in the population, generally speaking, apart from N. Haynes, where we have 24-hour recalls, I don't think there are so many studies, population studies, which use other sorts of self-reports. So we have 24-hour recalls. It could certainly be done for that. Food records, I think, would be a bit more problematic. But there may be some studies which have that sort of information as well. So in principle, yes, it could be applied equally well to other sorts of instruments. Whether or not it could be used in the a case where there are episodically consumed foods, I don't know, and one may have to do more sophisticated things along the lines that Victor Kipnis has already talked about, and we'll talk about in the next lecture as well.
Okay. I think that's a good way to close the question and answer session. I do want to point out that as you were talking, Larry, someone did send in a one last chat note that said, "Excellent seminar, thank you." So I just want to reiterate that sentiment, and I want to thank all the audience members for joining today's webinar. And we're really happy that we were able to keep Larry on the line throughout the webinar. That's not always the case in some of the practice runs we've done. So everyone, please join us next week for the last webinar in our series, which, as Larry just mentioned, Dr. Victor Kipnis will discuss assessing diet and health relationships